All right, so we're gonna first talk about large language foundation models. You probably already heard of this uh, terminology many times. So large meaning that this model, this categories of models have been trained or pre-trained on massive amount of data that can include everything and require millions of GPU compute hours. So there are many different data sources ranging from Wikipedia to other specific data sources that contains, you know, millions of documents, and these models are trained by using these massive amount of data. We call it language models because they have been initially designed for natural language processing tasks, such as language generation or summarization. And the a lot of the input data, the training data, are kind of based on language samples. Foundation, because we realize that these models can serve as a basis for many natural language processing tasks. And actually, it can go beyond text-based language processing. They can now do images and video. And these models are really the foundation of these new applications. Because these are neural network models. For example, they're based on the transformer model, so that's why we still call them models, neural network models. These large language models are increasing in terms of numbers, and many different contributors or vendors providing different models. On Hugging Face, you can find many different models of even the same model with the same name from different organizations or contributors. Ideally, each model comes with a model card that is used to describe the model itself in terms of the size and how this model has been trained, the performance, and the limitations of these models. For example, this is a snapshot of the model card from Meta's Llama 3 model. So it's a auto regression language model that use optimized transformer architecture. How many tokens they have in their vocabulary, and how many tokens they use to train to build the transformer architecture. So many details. Also, what's interesting is that they provide information about their knowledge cutoff. Essentially, this is the date of the training document they used to train a model. So if you will be interested in learning or querying information that happens after this date, and then the output from the model may not be very reliable. And also, as you can see here, they describe the training data for Llama 3. It is pre-trained over 15 trillion tokens of data. We'll talk more about the tokens. And then, of course, you can find some benchmarking numbers, especially they want to show the progression of different generations of their models. Okay, so what is tokenization? Tokens are foundational units. So it's like the atoms of large language models. Tokenization is the process of translating strings, for example, your input text prompt, and converting them into sequence of token, and vice versa. So tokenization is a set of libraries that has been pre-designed. You can actually train tokenization modules, but that's a different story. But typically you have a tokenization method that's agreed on, and then the models will be using the tokenization to get the input tokens for inferencing or for pre-training or fine-tuning. So what is a token? Token is the smallest unit that taken feed into large language model. If you relate it to the words in natural language, they are not equivalent. A token is typically not a word in natural language, unless you specifically using a tokenization method that treat words as tokens. We'll see that's an option, but it may not be the efficient option. So that's why in the available tokenization or tokenizers, the token is not equal to English or other word in other languages. You can think of tokens as pieces of words. For example, in English language, one token is approximately 4 characters or 3/4 of a word. As a reference, if you make the works of the books by Shakespeare, you're talking about 900,000 words used in those books, or 1.2 million tokens. So token is not equivalent to a word in natural language. It could be a smaller or larger than a word, depends on the tokenizer approach. You have options of using different tokenizers. There's a tool actually you can use to try different tokenizers. And one of them is the tick token. This is just one example that listed I believe it's the OpenAI's model page and the website. It uses an algorithm called BPE as a way to build their tokenizer. The Python library is called the tick token. So you can use, so if you import this tokenizer library, you can call their APIs, for example, get encoding, and then to check how the tokenizer can encrypt or encode the input text and then convert it back using a decode method. We'll see these examples in one of the notebooks we posted on our course website. And then what's important for choosing a tokenizer is about the performance. This figure shows that how this tick token tokenizer compared with a open source tokenizer. The x-axis is the number of CPUs you use to perform these tokenization operations. Basically, if you're given, if this tokenizer is given a large, a long text, how fast can this tokenizer break down the original text into this small unit of tokens? So this graph shows that if you increase the number of threads, how fast this tokenization process can be done. So as you can see, if we see if one thread, the tick tokenizer can achieve about 7 bits per second, megabytes per second, whereas the open source one is only about 1 or 2. And as you go further, the performance goes up, can scale up, but it reaches the peak performance when it gets to the 16. Okay, so yeah.
Do you choose the number of tokens, or is that something that develops as you're training your model?
So for tokenizers, you can actually, when you design it, you can set the vocabulary size. Some algorithms can converge on a size, but different tokenizers, you can expect that they have different vocabulary size. So next, we're going to look at a few options to build tokenizers. The first one, very intuitive, is the word-based. Um, so if you are given this sentence, let's do tokenization. It's an English sentence, and it implies that there's a space between these words, um, and you can split on spaces, which will give you these three tokens. For the same input sentence, if you split on punctuation, so these apostrophe and then this exclamation mark and also the spaces, then you get different set of tokens. So these are word-based. So you may have to use actual rules for punctuation so that you can deal with different input sequences. It may result some large vocabularies. For example, if you look at English language, you may end up having 500,000 words. So that means 5,000 different words will be the vocabulary of your tokenizer. So that's a lot. Um, so why we have that many? If you use the space or punctuation marks, then this word dog will be different, will be treated differently from this dogs word. So that's why you have a lot of these uh, different tokens, although they could be somehow recognized as the same word or category. For unknown word, you need a customer token to represent words that's not seen before in the vocabulary. The other tokenizer, as example we show here, is called character-based. So based on name, okay, we're going to treat every character as a token. So we're going to have a lot of tokens now. As compared to the word-based, if you use character-based, then you have, so this is more than 2,000 of tokens for that same sentence. The benefit is that the vocabulary is much smaller. Essentially, they're talking about the 26-inch words with spaces, punctuation marks. You can imagine the vocabulary is much, much smaller. So you have much fewer out of vocabulary or unknown tokens. The drawback is the representation is less meaningful. As you can see that if you treat these as individual characters, it's very hard, or it's going to be very hard for any neural network model to make connections or determine their relationships among these different tokens. And there's a kind of exception for Asian languages such as Chinese, which I'm very familiar with. If you treat every Chinese character as a token, it may work because in Chinese language, each Chinese character represents a meaning. So it's different from these alphabet in English languages. Each one doesn't really represent a specific meaning. Yeah. And if you do this character based for the same sentence, you can see that you have a lot more tokens to be processed by a model. So that's another drawback. So we can do something kind of compromise between the word-based and the character-based. So here now we have the sub-word-based tokenizer. So frequently used words should not be split into smaller subwords, but rare words should be decomposed into minimal subwords. So here's an example. If we have annoyingly, it comes from annoying. So even this might be a rare word, but we better decompose it to these annoyingly and ly, because ly is a kind of suffix that can be used in other word compositions. So for the same sentence that we saw earlier, the tokenization can break it down to these different categories. and this brackets for slash W is basically a special word that represents the white space. If we can build a tokenizer that do this type of subword based separation of the input text into smaller units, the tokens, then we can have some benefits compared to the first two tokenizer methods. The subwords end up providing a lot of semantic meaning. As you can see, each of these 5 tokens have some meaning. For that word tokenization, it actually break that down nicely into these 2 parts. Token is a word that you can expect that will appear in many other places in the same document. And ization, this is again a suffix that can happen in other type of words as the suffix. Also, this type of subword-based tokenization can have good coverage with small vocabularies and close or to no unknown tokens. So you can imagine that we'll definitely have a vocabulary that larger than the character-based. Character-based, you basically have the smallest vocabulary possible. But with this subword, you have a lot more, but it will be much fewer than the 500,000 tokens that you have for the first word-based. This is useful in some languages such as Turkish, where you can use these to form arbitrarily long complex words. Now, more generally, especially the recent development of different tokenizers, people have gained a lot of experience. So there are several, especially these 3 are very popular, actually widely used. First is called byte pair encoding. This tokenizer algorithm was initially developed by OpenAI when they pre-trained the GPT models. So if you use Chat GPT or GPT models, you can expect that they use this BPE as a tokenizer. Word piece is another one. This algorithm was developed by Google to pre-train BERT, which is one of the large language models. The models from Google, the Gemini or Gamma models, are using these tokenizers. Sentence piece is another one used in many different models. Okay, so you probably saw these several similar lines in those examples we posted on our GitHub repo. This tokenization process is done by the tokenize method for the tokenizer. You can use the transformers library from Hugging Face to import a module or a class called auto tokenizer. And using auto tokenizer, you can load those pre-trained tokenizers. This one is BERT-based case, and there's actually a BERT case-based uncased. So this is case sensitive. So this is an already trained tokenizer. So what do we mean by already trained tokenizer? Building the tokenizer is also time consuming because you need to give the tokenizer a large amount of data so that it knows, okay, these are the words that may appear in a document. So you can then, based on the algorithm that you choose, BPE or word piece. So these algorithms will run on these samples, try to see, okay, what will be the ideal tokens that we should set for that tokenizer. So it's a learning process, which takes time and resource, and that's why there are a lot of pre-trained tokenizers like this one. They are trained by some other organization, contributing to the community. So you can load that pre-trained tokenizer. And then that tokenizer will be able to kind of translate your input text, generate the tokens. This auto tokenizer from pre-train will be able to use the name of the tokenizer and then instantiate a object called a tokenizer. Kind of confusing. The tokenizer is just, you can name it A or B. This is just a variable name that you can of course replace with something else. So this tokenizer will be the instance that you will use to make these API calls to perform the tokenization operations. So let's say your input sequence is this sentence. You would call this tokenizer dot tokenize, which is it's one of the functions, and then use this sequence as the input argument, and that will return tokens. And I can print the tokens. You expect to see something like this. So this is the input prompt or the sequence. You can see that this sequence is being tokenized, and 1, 2, 3, 4, 5, 6, 7. So 7 tokens are coming out of this input sentence. And you can see that it's kind of word, but here transformer is now converted to this 2 tokens, transform, and this special character ER. You don't have to really know why this is printed this way, because it's a special character. So this 4 characters are actually is part of a token. And also because this ER as a token, and that happens after a word. So you can imagine this will be helpful, because this ER as the last 2 characters could appear in many other words. So it makes sense that this is a separate token. Okay, so tokens are the smallest unit that we break the input sentence into. But for the model to process in the next step, we actually need to convert them into a numerical representation. And each token is represented as an identifier. So we can call this convert tokens to IDs using the token that we got earlier as an input. So that function will convert these recognizable, readable tokens into these IDs. So these are the token IDs that will be used for the next step. Because the dealing with individual characters or words or subwords is not as convenient if we convert them into these numbers. So these IDs kind of one-to-one mapping to these tokens, token IDs. Okay, so just to give you an idea of what we're talking about at this point, we are getting ready for these input sequence to these transformer model or any machine learning models. This tokenization process or the tokenizer is to convert text inputs into vectors for machine readable machine learning processing. As you can see, this input sequence from a sentence, we will have these tokens generated. And in fact, the machine will be able to recognize these token input IDs. This example here looks like they're using word-based tokenization, but we in reality, a lot of the tokenizers, modern tokenizers, are using the subword based. So it just happened that these words just map to these tokens. But in reality, some other words may be broken down into multiple tokens. So I have some pointers that you can maybe read more